Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When we look at the vast, silent expanses of the Arctic and Antarctic, we often perceive them as frozen in time, static landscapes of white and blue. However, beneath the surface of the frigid water, a complex physical symphony is playing out. This is the story of the Bernoulli Frequency, a phenomenon that turns massive icebergs into giant musical instruments and provides a secret countdown to their eventual collapse. To understand this, we first have to look at the work of Daniel Bernoulli, an 18th century mathematician who discovered that as the speed of a moving fluid increases, the pressure within that fluid decreases. While we usually apply this to the wings of an airplane or the flow of blood through our veins, it applies just as powerfully to the ocean currents rushing around the jagged, underwater keels of icebergs. As deep-sea currents encounter the irregular surfaces of an iceberg's base, they are forced to accelerate. This creates localized zones of low pressure. If the geometry of the ice is just right, it creates a self-sustaining vibration. Think of it like blowing across the top of a glass bottle or the way a reed vibrates in a woodwind instrument. The iceberg begins to sing. But this isn't a song you can hear with your ears. These are infrasonic harmonics, vibrations with frequencies so low, often below 10 Hz, that they travel for hundreds of miles through the dense medium of the ocean without losing their energy. For decades, these low-frequency hums were a mystery to oceanographers. They were often dismissed as tectonic background noise or even whale calls. But recent advancements in hydroacoustic monitoring have revealed a startling pattern. These frequencies aren't random. They are mathematically tied to the mass, shape, and structural integrity of the ice. When a glacier is healthy and solid, its Bernoulli frequency remains stable, a steady, rhythmic pulse that resonates through the water column. However, as the internal structure of the ice begins to fail, as microscopic fissures grow into massive internal voids, the tuning of the iceberg changes. This brings us to the concept of infrasonic harmonics. Just like a guitar string produces a higher pitch when it is tightened or shortened, an iceberg's harmonic profile shifts as it nears a calving event. Calving is the process where a large chunk of ice breaks off and crashes into the sea. Previously, this was seen as a sudden, unpredictable event. But by tracking the Bernoulli frequency, scientists have discovered that the ice actually enters a state of harmonic instability, days or even weeks before the break happens. The frequency begins to jitter or slide up the scale. This is the sound of the ice's internal bonds snapping at a molecular level, rearranged by the pressure differentials of the surrounding water. The predictive power of this science is revolutionary. By placing arrays of hydrophones, underwater microphones, around major ice shelves like the Ross Ice Shelf or the Thwaites Glacier, researchers can now listen to the health of the ice in real time. This isn't just about curiosity, it's about survival. Rapid glacial collapse is the primary driver of sea level rise. If we can predict when a massive section of ice, the size of a small country, is about to break away, we can better understand the immediate impacts on global ocean currents and coastal safety. Furthermore, the Bernoulli frequency gives us a window into basal melting. This is when warm water eats away at the bottom of a glacier from the inside out. This hidden melting is incredibly hard to measure with satellites, but it changes the way the ice vibrates. The infrasonic signature acts like a diagnostic tool, much like a doctor using a stethoscope to listen to a patient's heart. By analyzing these harmonics, we can map the unseen erosion occurring miles beneath the surface. The physics here is a beautiful reminder of how interconnected our world is. An 18th century principle of fluid dynamics is now the key to monitoring the most pressing environmental changes of the 21st century. The ice is talking to us, vibrating with the energy of the ocean, telling us exactly when it can no longer hold on. As we refine our ability to decode these infrasonic messages, we move closer to a world where the sudden disappearance of our glaciers is no longer a surprise, but a forecasted event that we can prepare for. This acoustic frontier represents the bridge between classical physics and modern climate action, showing that even the most silent places on Earth have a voice if we only know how to listen. For more incredible facts like this, don't forget to subscribe and turn on notifications.